Hi, my name is Jordan Mitchell. This is just a quick overview of my design for the InnovateFPGA contest. My design is an FPGA-based LIDAR. LIDAR is a method of measuring distances by timing how long it takes for light pulses to travel to some obstacle and bounce back. The design makes use of a D10 nano development board and a custom PCB which contains an infrared emitter and photodiode for sending and receiving pulses of light. This is the schematic of my design. To explain how the device works, let's first look at the circuit for driving the infrared light source. As you can see, it uses multiple GPIO pins connected by resistors to an emitter diode. The reason why I used multiple GPIO pins was because the required current was larger than the maximum that a single pin could supply. Now, let's look at the circuit for receiving the light pulses. The circuit contains a photodiode connected to a transimpedance amplifier that then drives the input of a comparator. The role of the transimpedance amplifier is to amplify the photodiode current fluctuations in the order of a couple of microamps to a suitable level to feed into the comparator. The comparator then converts the signal into a 3.3 volt digital logic output that is fed into a GPIO pin on the FPGA. On the FPGA fabric, the delay can then be calculated by using a relatively simple logic operation. Due to the low sensitivity of the photodiode and low power of the infrared emitter, ranging could not be made to work as the resolution was around 30 cm, but the device only had a 10 cm range. If I had more time, I would have attempted using proper lasers specifically made for this application, as well as highly sensitive avalanche photodiodes. Anyway, here is a video of the device performing proximity detection. As I place my hand in front of the light source, the LEDs on the FPGA turn on. We can also see the transmitted and received signals on the oscilloscope. The top trace is a 1 MHz square wave produced by the FPGA, which is driving the infrared emitter. The bottom trace is the signal received by the photodiode. Initially, the bottom trace is quite flat except for some noise, but when I place my hand in front of the device, the bottom trace matches the top trace, meaning that it has been detected by the photodiode. That was a demonstration of my entry into the InnovateFPGA contest. Thank you for watching the video.